Okay, in this video I'm going to follow up with the discussion we started in class today. There was a request to work through this second derivative equation, or computing the second derivative in this implicit form. And in looking over my notes, I noticed that I did miss a sign here in our conversation today. But I think what I'll do is I'll just start from scratch here with a new example that's on MathXL. And I noticed something that was kind of interesting with this particular example, and I don't know if this is going to show up every time that we see this style of question, or maybe it's just this particular example that was selected for us to use. But my new equation here is 14x squared plus y squared equals 9. So 14x squared plus y squared equals 9. Now if I want to compute the derivative, since this is an implicit function, we would go through the same process that we normally would. We'll find ddx of both sides of the equation, and 28x becomes the derivative of this term, plus 2y dy dx equals 0. So I think that's pretty straightforward from here. We can isolate this expression, essentially, the dy dx component, by subtracting 28x and dividing by 2y. So dy dx is 28x negative divided by 2y. So since there's a common factor of 2 here, I think we can call this negative 14x over y. So there's our first derivative in implicit form. Let's go ahead and find the second derivative, again by applying the ddx command, so the derivative command, to essentially both sides of the equation. So I'm ignoring this here in the middle for right now, but this dx of dy dx, well, that does produce our d squared y dx squared that we're looking for, our second derivative of y with respect to x. And we will use the quotient rule here. So the low function times the derivative of the high function minus the high function times the derivative of the low function, all divided by the low function squared. So again, no real surprises here. I think this is what we saw earlier today in class. If we clean this up just a little bit, the negative 14y becomes apparent at the beginning here. We'll add 14x times dy dx. Now dy dx we said was negative 14x over y, and we still have this y squared. So we ended up using this notion that dy dx is equal to negative 14x over y, and then we just back substituted in place of dy dx. So that's where this component came from. And again, I think we recognized that while we were chatting in class today. But something interesting that occurs, let me make some room here. Okay, so I had to make some more room for me to work down below. What I was going to say is that something interesting occurs when we make this distribution. Now, normally I'd be okay stopping here, and to be honest, I think that's a fine place to stop. But there's something kind of interesting with this particular form of the equation. I can't say that it always happens this way, but again, something interesting does occur. So I'm imagining this as a fraction, 14x over 1 times negative 14x over y. So that's going to become a minus 196x squared over y, and all of that over y squared. Again, this would be, I think, normally a fine place to stop. What the hint in MathXL was suggesting is, it'd be nice if we didn't have a complex fraction or a compound fraction here, if we didn't have this fraction inside of another fraction. So what we can do is we can multiply by some form of 1, and we're going to do so in the form of the fraction y over y. So what that's going to do is it's going to force us to distribute in a y to both terms in this numerator and in this denominator. And at first you may not see the benefit to doing that, but after we do just one or two steps, I think you'll start to pick up on what's going to happen next. So this y, when distributed in the numerator, produces a minus 14y squared. And then this y, when multiplying by this fraction, will essentially cancel the y in the denominator, and we're now left with minus 196x squared. And we can divide that by now y cubed. Okay, well again, not a whole lot better than what we saw before, maybe a bit simpler, but perhaps not even a whole lot better. But now what I would encourage you to look for is a common factor. And we actually have 14 that's acting as a common factor in the numerator. So I'm going to factor it out. Let's see. I don't know if I want the positive 14 or the negative 14. I'm going to go ahead and factor out a negative 14. So I'm factoring out a negative 14, and that leaves me with y squared plus 14x squared over y cubed. And again, you may not see it just yet, but when I had jumped back to the original, perhaps you did. Do you recognize 14x squared plus y squared? Well, 14x squared plus y squared shows up here again. So in this interesting factoring scenario, that y squared plus 14x squared, which we saw back here in the original equation, is really just equal to the number 9. So this y squared plus 14x squared is also equal to just the number 9. And so now we have negative 14 times 9 over y cubed. And I'm going to double check the math on that one. 14 times 9 is 126. So we have now negative 126 over y cubed. So I'll check that here in just a second with MathXL. I was okay with any of these answers back here while we had the multivariables, and I'm okay with them because that's the heart of an implicit function. We have a function that contains multiple variables, so I wasn't surprised to see a derivative or a second derivative that contained multiple variables either. But evidently, with a little bit of luck, I think in this case, and a little bit of extra effort with that factoring, we ended up being able to rewrite this second derivative simply in terms of y. So let's see what the MathXL site thinks. We now have, let's see if I can get this calculator up here, or this keypad, negative 126 over y to the third power. Yeah, and they ended up liking that one. So if you got an error message by submitting one of the second derivatives from back here, I'm curious what the error message was. Did it say that your answer is correct, but in the not fully simplified, or did they say that your answer was incorrect completely? Because I am kind of curious. In any event, for the test that we'll see on Thursday of this week, I'm not really all that concerned with this extra factoring steps down here. I'd be really happy if you correctly compute your derivative, your implicit derivative at the first order, and then if we ask the second order derivative in implicit form. So I'd be happy with that as well. If you've got further questions, try to catch me before school tomorrow. Otherwise, I'll see you for your test during fourth block. Thanks for watching.